What I'd like to talk about is Hecke algebras that should describe the Bernstein components associated to simple supercuspidal representation. So namely, take your group G, pick some levy M and G, and put simple supercuspidal representation on your levy. Unramified, you're allowed to unramified twist the simple supercuspidal, parabolically induce. You get some canonical Bernstein component associated to this data. And the philosophy is that there should be some Hecke algebra that describes this Bernstein component. So namely, there should be a Hecke algebra whose category of modules is equivalent to this Bernstein component. So that's what I'll talk about. So first I want to sort of review some background, which is probably covered in Professor Roche's lectures. So let F be a p-adic field, O the ring of integers, P maximal ideal. And for now, I just want to take G to be split connected reductive group. Let T be a split maximal torus. To define, I just want to recall the definition of Bernstein component. And for that, we need this definition of cuspidal pair. So recall that cuspidal pair is just the data of a Levy subgroup L and a supercuspidal representation of your levy L. So we can talk about equivalences of cuspidal pairs, namely two cuspidal pairs are said to be equivalent if the levies are conjugate, and up to unramified twists, the supercuspidals of these levies are also conjugate via the same conjugation. Okay, so what's this Bernstein component? Well, take an equivalence class of cuspidal pairs L comma sigma. The Bernstein component associated with this equivalence class is just the set of all representations pi, each of whose irreducible subquotients are subquotients of this normalized principal series, IPG of sigma chi, where sigma is this supercuspidal from this cuspidal pair, and chi is allowed to be unramified character of the levy. Okay, so again, let me just say again that the philosophy is that these Bernstein components should be equivalent to category of modules over some appropriate Hecke algebra. Namely, a Hecke algebra of functions on G which transform with respect to some compact open subgroup K, transforming with respect to a representation rho of that K. So not quite bi-invariant functions, not quite K bi-invariant functions, but sort of rho bi-invariant functions. So that's sort of a Hecke algebra that we're trying to find. And what's an example of this? Well, there's a classical result of Borel which says that if G is semi-simple and you take the levy to be maximal torus and chi to be the trivial character of maximal torus, then this Bernstein component is equivalent to the category of modules over Iwahori Hecke algebra. So this is just this trivial character. I is the Iwahori. Okay, so this was later generalized by Professors Morris and Roche to the so-called depth zero situation. And what I want to talk about is the so-called minimal positive depth situation. So namely simple supercuspidal representation. So again, we're going to put a simple supercuspidal representation on this levy M. So general levy. Okay, so for that I need to recall the definition of simple supercuspidal representation, and unfortunately I'm going to need a slew of preliminaries and notations, but hopefully that's okay. So now I'll let G be split simply connected, and this is the setting of Professors Gross and Reeder, their paper on simple supercuspidals. I should mention, however, that their work was generalized later by Professors Gross, Reeder, and Yu to the so-called epipelagic representations, and they don't really need to assume split simply connected anymore, and they allow for some higher depth as well. But anyway, we're going to assume split simply connected. Okay, so let phi be a set of roots of T and G. The set of roots of T and G, we have an apartment, a set of affine roots, affine vowel group W upper A. And I want to fix a Chevalier basis in the Lie algebra. So once we fix a Chevalier basis, then to each affine root we get an associated affine root group U psi, which is this is the notation I'll use. Isomorphic, these are just isomorphic to the ring of integers. These are affine root groups associated to each affine root. Okay, so I'm going to fix an alcove C in the apartment, and to such a choice C, we have a corresponding set of simple affine roots and positive affine roots, namely the affine roots which are positive on this alcove C. Those are these positive affine roots. Okay, and then we need to define some canonical subgroups in G and T. So let T0 be the maximal compact subgroup of T of F. And T1 is going to be the so-called 1 plus P points of T. So these are just elements of T0 such that every character lands you in 1 plus the maximal ideal. So this is the next level in the filtration for T. And I is just going to be this standard Iwahori associated with this alcove, namely the group generated by this maximal compact T0, and all the affine root groups U psi, such that psi is positive on this alcove C. So that's the Iwahori associated with this fixed alcove. C, where's C? C. And we have the pro-unipotent radical I plus, which is the same thing, but we're just going to put T1 instead of T0. This is this pro-unipotent radical. And finally, we need this I plus plus group to define simple supercuspidal representation. So this I plus plus group is really just the plus part of I plus, but one way to define it is just, it's the same thing, it's the same thing as the pro-unipotent radical I plus, but we're going to throw away all the simple affine root groups and just go sort of one level lower in the filtration. So we're throwing away U psi, where psi is simple affine root, but keeping U psi plus 1, where psi is simple affine root. So we're just going to go one level lower in the filtrations for the simple affine root groups. But it's really the plus part. Anyway, you can think about it as the plus part of this pro-unipotent radical. Okay, so the last piece of notation I need is, let's define this group H to be the center times I plus. And this is where the supercuspidals are going to be compactly induced from. And then just let N be the normalizer of T and G. Okay, so right before we define simple supercuspidal, we sort of need this structural result. So the group I double plus is normal in I plus with the following quotient. So it's a canonical direct sum of these affine root group quotients, U psi modulo U psi plus 1, where psi is a simple affine root. So it's a direct sum of these simple affine root group quotients. These are just FQ vector spaces. So this is anyway, this is completely canonical, and yeah, we're split simply connected. I don't know if that helps, but yeah, this is arbitrary characteristic. And the proof of this is not difficult. So it amounts to showing that this quotient I plus modulo I double plus is abelian. And that's really not hard at all. But I'll talk about that later, actually, when I define our Hecke algebra. We're going to have some analogous K plus and K double plus. And so I sort of we're going to have the same sort of structural result for in our situation. So I'll come back to this later. Okay, so what is a simple supercuspidal representation? Well, it's just it's a representation that's compactly induced from this H group. It's center times I plus of a one-dimensional character. That's all that a simple supercuspidal representation is. But not just any one-dimensional character. We need some condition of affine genericity. What does that mean? Well, character of H, so remember H is the center times I plus, we say that's affine generic if two conditions hold. Number one, chi is trivial on this I double plus. And number two, it's non-trivial on each of these factors. So we have this decomposition, and for it to be generic, it should be, well, affine generic, it should be non-trivial on each of these affine root group quotients. So namely, just non-trivial on each of the simple affine root groups. Okay. And the theorem is that if you take an affine generic character, the compactly induced representation from H to G of this one-dimensional affine generic character is supercuspidal. And those are what Professors Gross and Reeder call simple supercuspidal representations. So they're completely, they're very simple, and I'll do an example, I think, on the next slide. Yep. Okay, so this is really a very easy supercuspidal to define. So let G be the group SL2Q2. So the standard upper triangular Iwahori and the pro-unipotent radical I plus. And then we have this I double plus group. Remember, I just said throw away the simple affine root groups, but go one level lower. So these are, we're just going one level lower in the simple affine root group. So instead of O and P for I plus, we're just going to impose P and P squared. That's this I double plus. And what's an affine generic character of I plus? It just sends the matrix A, B, 2, C, D to -1 to the B plus C. That's a simple, that's an affine generic character. And in fact, it's the only affine generic character for SL2Q2. And then what the result says is that this compactly induced representation is supercuspidal. So that's the only simple supercuspidal representation of SL2Q2. Okay, so let me remind you what we're trying to do. So we're trying to find a Hecke algebra, a canonical Hecke algebra that describes these Bernstein components. And a priori, there's no reason to be able to guess what sort of compact open this should be, and as well what rho should be. But that's part of this work, is to sort of find a canonical Hecke algebra that describes these Bernstein components. So what are the goals? Well, I just said the first goal is to figure out what K and rho should be. Given a simple supercuspidal representation on a levy, we need to figure out what this Hecke algebra should be. And then the next goal is to compute and describe this Hecke algebra. So namely, figure out generators and relations for these Hecke algebras. And hopefully, they turn out to be some classical affine Hecke algebras. Okay, so for the rest of the talk, I'll mostly focus on the group SP4 with, well, it has two levies. So first I'll talk about this levy SL2 cross GL1, but we recently figured out that there's sort of a nice and elegant way to approach this problem, which really works for general groups. So part of the discussion will be towards understanding how to do things generally, but I'll focus on a nice example, which is really the example that I understand completely. But anyway, I'll say things as generally as I possibly can. Okay, so let G be the group SP4 and consider this levy SL2 cross GL1. So again, what do we want to do? Well, we take a simple supercuspidal on this levy. So let's take a simple supercuspidal compactly induced of chi on this SL2 and a character mu of GL1. So we have this representation on the levy. And for now, actually, I'm going to throw away, I'm not even going to consider this data of this representation on the GL1 part. All I really need is this simple supercuspidal on SL2. Later on in the talk, I'll bring back this GL1 part of the levy. But for now, I really don't need it. Okay, so how do we figure out what this Hecke algebra should be? Well, there's this general theory of covers and types from Bushnell and Kutzko, which I don't really understand anything about. But what I do know is that theoretically what you're supposed to do is you're supposed to take this inducing representation, so this supercuspidal should be compactly induced on the levy, and you're supposed to take this inducing representation, so in our situation it's chi, and sort of extend it as much as possible in your ambient group G. So it's living on some subgroup of the levy M, and we want to extend this as much as possible within the ambient group G, so within SP4, some compact open K and SP4 with some nice properties. That's pretty much all I know about this theory of covers. But anyway, so let me fix some notation. Let alpha and beta be the standard set of simple roots for SP4, beta the long simple root, alpha the short root. And this levy corresponds to this long simple root, so this long simple root beta. So this affine generic character, remember, it lives inside SL2, and in particular, it lives on the simple affine root groups of SL2, so namely U beta and U1 minus beta, and trivial on the next level down in filtration. So it's just non-trivial. It's just a character of this product that's non-trivial on each factor. But anyway, it lives on U beta and U1 minus beta. And there's also, remember this group H, so it's compactly induced from this group H. There's some center in H. So namely, there's some central character for this simple supercuspidal. But again, I don't need to worry about that for now. I'll bring that back later on in the talk. It's really unnecessary for now. Okay, so so how do you extend, or how did I sort of start out, approaching this problem? Well, in order to take this character chi, which lives on U beta and U1 minus beta, and in order to extend it to some compact open subgroup K and G, the most basic thing to do would be to just literally leave it on these root groups U beta and U1 minus beta, and just take it to be trivial everywhere else. So there are these other root groups, let's say U alpha, U gamma, U delta, and then there are negative root groups. And I just want to take it to be trivial on those other root groups. So have it just living on these affine root groups U beta and U1 minus beta. That's the most basic thing to do. Okay.
Do you have a parabolic for the covers?
Sorry?
The theory of covers, do you have a parabolic circle?
I'm not sure. So I don't know anything about, again, I don't know anything about this theory of covers. But anyway, this is the levy. I mean, this is the levy that I'm considering. Yeah, I don't know if that answers. I mean, yeah, so we're talking about parabolic and, yeah. Sorry?
Can you just say whether it's the Klingon or the Siegel parabolic?
Well, it's the parabolic with this levy, SL2 cross GL1. Yeah. Klingon, okay. Maybe that's the right name. Okay. Yeah. Okay, so we're trying to extend this character chi within the group SV4. Well, you can't just, I mean, this is not well defined just by defining it to be trivial in other root groups. In order for this to be a well-defined character, we need chi to be trivial on the commutator subgroup of K. It's not hard to see. And, okay, so what I did was I brute force, and so this is why I'm calling this sort of not so elegant approach to finding K and rho. First thing that I did was I just brute force computed the commutator table of SP4, and I just stared at the commutator table to see where this character chi that I defined within SP4 is trivial on commutators. If you stare at the commutator table for long enough, you get the following subgroup K, which is canonical index P subgroup of this I plus group. Namely, instead of integral entries in the upper right and maximal ideal in the lower left, you just impose the condition of putting the maximal ideal on this U alpha, so this is the U alpha root group, where I have P's in these entries. So it's just I plus, throw away the affine root group U alpha, but we're just going one level lower in this affine root group. So just, yeah, this is this index P subgroup of I plus. So that's where this character chi naturally extends, this affine generic character naturally extends. Okay, what is this, in other words, what is this compact open K? Well, look at the standard affine apartment for SP4. Here, this lower triangle is going to be fundamental alcove, so this lower green line is alpha check. This upper green line is going to be beta check. And remember, this affine generic character was supported on U beta and U1 minus beta. So here's our standard alcove. And what K is, it's just the intersection of the pro-unipotent radicals of these two alcoves, or these two Iwahoris. So you have these two canonical Iwahoris which border each other, and K is just the intersection of their pro-unipotent radicals. In other words, it's the pro-unipotent radical of the parahoric associated to this point. Okay, so again, this was really this was an ugly way of doing things because I computed commutator tables, so I really want to get away from that. So here's a more elegant approach to finding figuring out what this Hecke algebra should be. So what I just showed was what this k and rho is. It's namely this affine generic character canonically extended to this k. But here's a better way of doing things so that it works. We can do this much more generally. Okay, so in order to start talking about this, I want to redefine or give an equivalent definition of these I plus and I double plus groups. So namely, take, as Professor Gross was talking about yesterday, let x naught be the unique point in the alcove on which all simple affine roots agree. So this is this barycenter of this fundamental alcove. So that's x naught. So they have common value 1 over h, where h is the coxeter number of G. So this is where, again, this is where the simple affine roots of G take the same value, 1 over h. And what is I plus and I double plus? Well, I plus is just this Moy-Prasad subgroup at x naught, comma 1 over h. And then, as I said earlier, I double plus is the plus part of this pro-unipotent radical. So it's at 1 over h plus. What does that mean? Well, it means that I plus is generated by this group T1, T of 1 plus p, and all the affine root groups U psi, where psi takes the value greater than or equal to 1 over h at the point x naught. And I double plus is just the same thing, but we have a strict inequality. So all affine root groups U psi, where psi takes the value strictly greater than 1 over h at the point x naught. It's another way of defining this I plus and I double plus group. And the reason why I want to do this is that we're going to have, to sort of find this Hecke algebra more generally, we're going to have an analogous k plus and k double plus, which is defined completely analogously. So how do we define k plus and k double plus? Well, we have a simple supercuspidal on our levy. So instead of what we did here, which is take the simple affine roots of G and see where they agree in the apartment, we have this levy M, a simple supercuspidal on the levy M. Let's take the simple affine roots for M. This is the key point. Take the simple affine roots for M and see where they agree in this ambient apartment. Okay, so again, we have this simple supercuspidal on M, and we're going to do something slightly different. So Professor Gross talked about taking maybe subcollections of affine roots and seeing where they agree, and these were some nice points in the apartment. These were some nice barycenter points of various facets. But instead of taking subsets of affine roots for G, we're just going to take the simple affine roots for M and see where they all agree in this ambient apartment. Okay, so okay, that's exactly what I just said. And let's say they take the same value, say 1 over M. And this is, we're going to define k plus and k double plus in exactly the analogous way as I plus and I double plus. So the simple affine roots for M, if you consider where they all agree in this ambient apartment, you're not going to get a unique point anymore. If you took the simple affine roots for G, you get this unique point, this barycenter of this fundamental alcove. But if you take the simple affine roots for M, you're going to get maybe some subvariety, some linear subvariety or something like that, not just the unique point where they all agree. But what we'd like to do is find some nice points, why not, on this subset. So what does nice point mean? Well, we're just going to say nice point means that all affine roots should take value 1 over mz at this point, why not? So we're going to try and find some nice point, why not, in the subset. And we're going to, this is what a nice point should be. Why should that be nice? Well, that's a nice point because the Moy-Prasad filtrations look nice if you impose this condition. So namely, when I define k plus in 1 second, k plus is just going to be the first Moy-Prasad subgroup at that point, why not? Okay, so here's the definition of k plus and k double plus. It's going to be the completely, so we have this nice point, whatever that means, on this subset where all the simple affine roots of M agree. It's going to be generated by T1, and exactly the same analogous thing. All the affine root groups U psi, such that psi takes the value greater than or equal to 1 over M, which was this common value of the simple affine roots. At this point, why not? and k double plus is just going to be the plus part. So generated by T1 and all the affine root groups u psi, where psi takes the value strictly greater than 1 over m. At this point, why not? And then canonically, you get the following analogous structural result, which is that if you take this quotient, well, first of all, k double plus is normal in k plus, and the quotient is isomorphic to the following thing. So we constructed this precisely so that the data of an affine generic character on this levy sits in this quotient. So namely, what do we have? We have the direct sum of all affine root group quotients u psi modulo u psi plus 1, where psi is a simple affine root for this levy. And that's exactly what allows you to define an affine generic character. I mean, an affine generic character for this levy is exactly a character of this first group, which is non-trivial on each factor. So we set things up exactly so we could pick an affine generic character for our levy. You're also going to get some other stuff, other affine root group quotients, but we actually don't care about that because what we can do is, if we have a simple supercuspidal on our levy, well, what is it? That's the data of an affine generic character. That's just a character on this group, this first group. And if we take trivial character on this junk, this affine generic character will canonically extend to our group K+. So that's, sorry. Sorry?
Could you get rid of that extra piece by a clever choice of why not? Or is it always
This is actually always here. Regardless of why not, we're going to get this same decomposition. Yeah. And maybe a better way of writing this is that k plus modulo k plus plus is just the direct sum of u psi mod u psi plus 1, where psi takes the value exactly equal to 1 over m at y naught. Because we're modding out by stuff that's strictly greater than 1 over m. So really, if you want to think about this another way, it's u psi mod u psi plus 1, where psi takes the value exactly equal to 1 over m at y naught. Okay, so what's the proof of this? It's analogous to I plus mod I double plus. Namely, you want to show that this quotient, it comes down to showing that this quotient is abelian. You really just look at commutators. So if you take u gamma, some affine root group in K plus, and u gamma prime, another affine root group in K plus, well, this is just this is their commutator. Commutator lives in this product. But the point is that gamma and gamma prime, since u gamma and u gamma prime live in K plus, gamma and gamma prime take the value strictly greater than or equal to 1 over m. At this point, why not? And so any non-trivial combination, so this is a product over I gamma plus j gamma prime, where I and j are greater than or equal to 1. Anyway, any non-trivial combination is going to be strictly, oops, that's a typo. It should be 1 over m plus 1 over m greater than 1 over m. Anyway, it's not difficult to show that this commutator subgroup is in this k double plus group. And so you get this abelian quotient. Okay, so what's the upshot? The upshot is that if you have an affine generic character for this levy, namely it's sitting here on this direct sum, it canonically extends to this k plus. And that's from this theory of covers, that's sort of what you'd like to do. Extend this inducing representation from the levy to something ambient in your overall group G. So that's our analogous K plus and K double plus. Okay, let's do an example. So here's our group SP4 with levy SL2 cross GL1. Remember, this affine generic character was supported on U beta and U1 minus beta, these simple affine root groups. So here are the hyperplanes. Here's H beta, this horizontal hyperplane, and H1 minus beta is the hyperplane right above it. So again, we're looking at where the simple affine roots of the levy take the same value. Well, beta and 1 minus beta take the same value on this middle red line. That's this subset that I was talking about. It's not a unique point anymore. So this isn't going to be a unique point like it was for this I plus or this Iwahori. And so, as I said, we want to find some nice point, why not, on this line. Okay, well, what are the nicest points on this line? Well, the nicest points on this line are really the points that cross hyperplanes. With respect to, if you're thinking about Moy-Prasad filtrations, you don't want to take some interior point which has some irrational values or some crazy rational values. Really, the nicest points on this line are the ones that cross hyperplanes. So namely, these points. We want to pick out some points here. Oh, really, there are two types of points. There are points that lie on vertical hyperplanes and points that lie on diagonal hyperplanes. But if you take, how do we narrow it down? If you take points on vertical hyperplanes, well, there are simple affine roots. So I should have mentioned, what's this common value? So remember this middle line. I should have said that where these simple affine roots of the Levy agree is on this middle red line, and they take the value 1/2 on this middle red line. Okay, so, well, we can throw away these points on the vertical hyperplanes for the following reason. There are affine roots that take the value 1/4 on these vertical hyperplanes. And so from the definition of K+, if you take a point on this vertical hyperplane, well, the Moy-Prasad filtration is going to have jumps at 1/4, 1/2, 3/4, et cetera. And our K+ is not going to be the first Moy-Prasad subgroup in the filtration. So the only way to do this is really, as I said, this condition here, that affine roots take, oops, maybe it's further back, that affine roots take the value in 1/mz, which in this case is 1/2 z. If you take a point on a diagonal hyperplane, then this K+ is going to be the first Moy-Prasad subgroup in the Moy-Prasad filtration. So that's what we mean by nice. And I'll give an example later. So for the other Levy, unfortunately, that doesn't narrow down. I mean, that doesn't pin down this condition that K+ be the first Moy-Prasad subgroup doesn't pin down the point for this other Levy. So I'll give that example later. But in any case, so this, yeah, the point that I mentioned before, using the so-called ugly approach, is exactly the point that we get. And then K+ is just the first Moy-Prasad subgroup in the filtration. So that's where the affine generic character extends. Okay, so so now I want to talk about the structure of this Hecke algebra. Yeah. Oh. So I want to, yeah, so I'd like to analyze this Hecke algebra for SP4, or maybe these general Hecke algebras. And to do that, I need to talk about the support. So the first thing to do in figuring out what this Hecke algebra should be is really to cut down the support of the Hecke algebra. So this Hecke algebra, in particular, functions are going to vanish on a slew of double cosets. And so what I want to do is cut down, I want to cut down the support. I want to figure out which double cosets functions don't vanish.
You mean the support equals F for some N?
Sorry? Sorry?
Not containing F for all.
Let's see, do I have a typo here? So, no, I think this is fine.
For a typical double coset?
F is a collection of double cosets.
Oh.
Sorry. So this calligraphic F is just a collection. It's a set of double cosets where functions don't vanish. So anyway, maybe that's horrible notation, but okay. So that's the goal first, to cut down the support. And how do we do that? Well, we need to understand these double cosets. So first of all, we have this decomposition, G equals I plus N I plus. I plus, remember, is the pro-unipotent radical of the Ihori, and N is the normalizer of the torus. And because of that, remember, this K plus was sitting in I plus index P, where we just, instead of integral entries on these positive root groups, we just put, we did the same thing, but maximal ideal on this U alpha root group instead. And so any double coset for I plus is represented by an element in the normalizer, but for K plus it's represented by X alpha and Y alpha, by these types of elements where X alpha and Y alpha are in this short simple root group U alpha, or affine root group. Little n is an element of the normalizer. Okay, so we want to compute what functions in this Hecke algebra, what they look like on these elements, on these representatives. So that's exactly what we want to do. We want to compute f of such elements for any function in this Hecke algebra. And what's the strategy? So the following is the strategy. So to figure out whether f vanishes on one of these elements, we just do the following type of trick. So remember, f transforms with respect to this character chi, or maybe I called it rho, maybe it should be rho now, on this compact open k plus. And so we want to bring something in from k plus from the outside. So let's bring something where chi is trivial on this x gamma, which lives in k double plus. Just bring it into f and commute it past x alpha and y alpha to hope that you get something non-trivial on the other side, chi of x beta. And so you just get something, this f of x alpha and y alpha is something non-trivial times the same thing, and you just get vanishing. Anyway, I'll do an example on the next slide. But this is sort of the strategy. You want to pull something in trivial from the right, pull it across to get something non-trivial on the left, and you get that function vanishes on this element. Okay, so let's just do an example. So here's the picture again. So here's our point, why not? And these are the hyperplanes h1 minus beta again and h beta. You can think about these hyperplanes as the affine root groups as well. You can think about the affine root groups u beta is living here and u1 minus beta is living on this upper hyperplane. And we want to see how the affine vowel group just transforms these root groups, these affine root groups. Okay, so suppose I want to compute something like f of n. So f of some normalizer element. And the proof of computing the support is going to be completely geometric. You pretty much just stare at the apartment and you know what the support of this Hecke algebra is going to be. So suppose I'm going to forget about these x alphas and y alphas for now. And this, by the way, this argument is going to work much more generally. So you really don't need to visualize anything in general. But suppose we take an element of the normalizer, little n, which sends these two hyperplanes, these two horizontal hyperplanes, to these vertical hyperplanes. Let's call them h gamma and h gamma prime. Well, the point is that one of these affine roots, let's say gamma, so let's say this hyperplane h gamma, one of these affine roots is going to take the value strictly greater than 1 over m on this point. One of them is going to satisfy this. So let's just say gamma takes the value strictly greater than 1 over m on this point, why not? And what does that mean? That just means that u gamma, so that just means that u gamma is contained in k double plus. That was the definition of this k double plus. And so we just compute. So just a simple commutation, f of n is f of n times this chi of x sub gamma, so some element of this affine root group u gamma. Remember, chi is trivial on this k double plus group. And we just want to commute it past. So we can bring this in, f of n x gamma. And it commutes past, so this is just what we do. It commutes past to give you something like x beta, or maybe x1 minus beta. So the point is that this element of the normalizer sent these two hyperplanes, these two horizontal hyperplanes, h beta and h1 minus beta, to h gamma and h gamma prime. And so conjugating this x gamma is going to give you something in these root groups, these affine root groups, u beta or u1 minus beta, where chi is non-trivial. Okay, so, and let's just say it's just this something in u beta, so you get some chi of x beta f of n. And this is just the strategy. So chi is non-trivial on these affine root groups u beta and u1 minus beta. And just visually, you can see that f is going to vanish on this element of the normalizer. And this is the argument for basically the entire support. There's maybe one special case that you need to take care of, but this is really, and the special cases amount to some finite vowel group thing, so you can really do this by hand. Okay, so what do you get in the end? You get that the support of this Hecke algebra is k plus n delta k plus, where n delta is the part of the affine Weil group, the part of the affine Weil group that preserves this middle line. So namely, horizontal translations and affine reflections through vertical hyperplanes. So it's, let me just go back. It's the part of the affine Weil group that preserves this middle red line that I drew before. That's what the support of this Hecke algebra is going to be. So it's supported on these double cosets represented by horizontal translations, affine reflections through vertical hyperplanes, and products of such things. Okay, so natural question, what about the other Levy GL2 and more general groups as well? So, okay, let's just talk briefly about this other Levy GL2. So this corresponds to the other simple root alpha. So now we have an affine generic character chi, which lives inside GL2. So it sits on U alpha and U1 minus alpha. So alpha is the simple root for GL2. So it's on U alpha, U1 minus alpha. And you consider the exact same setup. So let's take compactly induced representation from this Zi plus to GL2 of affine generic character chi. And right now, we're actually outside the situation or the setup of gross reader. So in particular, this compactly induced representation is not irreducible anymore. So the paper of gross reader is for split simply connected. We're outside the situation, but it turns out that this compactly induced representation splits up into two supercuspidals. And we're just going to call these simple supercuspidal representations. Okay. Okay, well, forget about that. We're trying to find some canonical Hecke algebra to describe this data. We have this affine generic character chi, which lives on Zi plus and GL2, and we want to extend it again to some subgroup of SP4. That's this covers business. So what does it extend to? Well, if you have the same picture before, it extends, this is sort of the not so elegant approach, which I started off with again. It extends to the pro-unipotent radicals, the intersection of the pro-unipotent radicals of these two Iohoris. So you have these two canonical Iohoris given by these red open triangles, and it's the intersection of their pro-unipotent radicals. That's what chi naturally extends to. In other words, the pro-unipotent radical associated to this point. Okay, so what's the support of the Hecke algebra going to be? Well, remember, chi is supported on, so this affine generic character is supported on the affine root groups U alpha and U1 minus alpha. And here are the hyperplanes H alpha, I should have drawn those, H alpha and H1 minus alpha. And in analogy with the other example, and this is really how it's going to work in general, the support of the resulting Hecke algebra is just going to be the part of the affine Weil group that preserves the middle line, this middle line. So remember, the sort of more elegant approach was to take the simple affine roots for the Levy. Here they're alpha and 1 minus alpha. And where do they agree? Well, they agree on this middle red line. I didn't draw it, but it's the middle, the line in between these two blue lines. And the support is just going to be, I haven't really worked this out completely, but this is something maybe I'm currently working on. But the support is just going to be the stuff, part of the affine Weil group that preserves this middle line. Okay, and again, so this was sort of this is a different example than this other Levy. How do you do this more elegantly? Well, you figure out where these two simple affine roots on the Levy agree. They agree on this middle red line, which I just mentioned. And you want to find some nice point on this line to define our K plus, or our parahoric, if you'd like. Well, again, there are two types of nice points, these red dots. But unfortunately, my definition of nice before, which is that K plus should be the first Moy-Prasad subgroup attached to a point, doesn't rule out. So now there are two types of dots, and it doesn't rule out any of these points. So so this is something I'm currently working on and trying to figure out what why we should consider one point over another. But from our perspective, there's really no reason to choose one of these diagonal points as opposed to a point on the intersection of these two hyperplanes. But if you compute, if you look at the commutator table sort of tells you to take one of these diagonal points. I actually haven't thought about whether, maybe I should think about this other point with respect to commutators or something like that. Okay. Anyway, this is sort of a funny example, which I'm still trying to understand. Okay, I'll just do one more example. So let G be the group G2 and consider this GL2 levy given by the long simple root. So we have some affine generic character chi sitting inside this levy GL2, and we want to extend, so the same thing as before, we want to extend this character chi to some subgroup of G2. You do the same thing as we did earlier. So what does it extend to? It extends to, well, this lower right triangle is this fundamental alcove, and these green lines are these roots, these co-roots. And this affine generic character chi extends to the pro-unipotent radical, the intersection of these 4 pro-unipotent radicals now. So it's an index, it's going to be an index Q squared or P squared subgroup. Yeah, sure.
I didn't memorize it last time.
Sorry.
Okay, I'm done.
Oh, you don't? Okay. Sorry. So this affine generic character chi extends now to a P squared, index P squared subgroup. It's the intersection of these 4 pro-unipotent radicals. We get this nice little diamond here. In other words, it's the pro-unipotent radical of this, at this point, the intersection of this vertical and horizontal hyperplanes. Maybe there's some other hyperplanes there, I can't. Maybe there's another one, I don't know. Probably not, actually. Okay, here's the picture of the support. So again, here's where our character extends to. And these 2 blue lines represent where the affine generic character chi is supported. It's maybe U beta and U1 minus beta, or I forget anyway, I forget what sort of notation I was using, but the affine generic character lives on the root groups, the affine root groups associated to these 2 hyperplanes. And so it's actually a really nice picture. So the support is just going to be, again, the part of the affine vowel group that preserves this middle line. Which time do I have? Okay. Okay, so that's the G2 example. So now I sort of want to finish off this talk by saying what this Hecke algebra is in the group SP4 and this levy SL2 cross GL1, but I'll say something about this other levy as well. So let's come back to this group SP4, levy SL2 cross GL1. So remember, I didn't touch this GL1 factor at all. So let's bring that back. So now, instead of talking about K+, I want to consider as general a Hecke algebra as possible for our group SP4. I mean, we don't want to just take trivial character on GL1. We want to allow for more general characters. So I'm going to enlarge to have as general Hecke algebra as possible. I want to enlarge K+. So stick, so we have this GL1 part of the levy, stick GL1O, as well as, remember, there's this central character for this simple supercuspidal on SL2, which I completely ignored before. Let's bring that back. So we have the center of this SL2 part of the levy, and now we want to consider this compact open K in G in SP4. Okay. So again, I want to put something on this GL1 part. Let's take a quadratic character of this GL1 factor. Now I take quadratic character because if you just calculate, similar to this calculation I wrote on the board, if you take some other character, which is non-quadratic and non-trivial in particular as well, you'll get that the Hecke algebra degenerates. So the support is going to degenerate. So really, this is the most interesting situation. So maybe I won't say anything about that. But anyway, if you take something else, you're not going to get something very interesting. Okay, so now we have a character, let's call it eta of K. So we take this chi on K+, remember this affine generic character which extended to K+, had some central character, we have that on z beta, and then we take this mu and combine it with chi to get this character eta of this enlarged compact open K. We want to consider the Hecke algebra with respect to this data. Okay. So it turns out that the support is exactly the same as before, and so we can really so it's this just this affine Weyl group of SL2. And what I want to do is I just want to show that this Hecke algebra is really a classical affine Hecke algebra, this Hecke algebra of type A11. So let's normalize some measure on G such that the volume of K is 1. We have some unit of our Hecke algebra 1 sub K, supported on the trivial double coset. And let's consider two functions in our Hecke algebra which are supported on these affine Weyl group elements which generate this SL2 affine Weyl group. So let me just draw the picture. We have, so remember we have these two horizontal hyperplanes, H beta and H1 minus beta. And remember the support was just the stuff that, the part of the affine Weyl group that preserves this middle line. This is just some SL2 affine Weyl group. It's exactly the affine Weyl group corresponding to horizontal translations and these vertical affine reflections. And in particular, so we have this, let's have some origin. This is our origin here. We have these two canonical generators, let's call it, so we have hyperplanes H delta and H1 minus delta. These are these vertical hyperplanes. We have two canonical generators of this affine Weyl group, so W delta and let's say W1 minus delta, reflections through these two hyperplanes. And we just want to consider these functions F delta and F1 minus delta, which are supported on, on these affine reflections. And what I'm going to show, or I'm just going to sketch that these two functions generate our Hecke algebra. So the function supported on these two affine reflections. And that'll go towards showing that this Hecke algebra is really this A11 type Hecke algebra. Okay. All right, so in order to talk about these quadratic relations, I need to define some complicated Gauss sum, and it's completely unimportant what this is. It beautifully comes into the quadratic relations. I mean, if you compute quadratic relations here, this Gauss sum just spits out at you. So it's, anyway, I need to define this to say what the quadratic relations are. Okay, so this is just some Gauss sum. And the result is that if this character mu on this GL1 factor is non-trivial, then you get the following quadratic relations. You get f squared, so this one of these generators, f squared is some constant times the identity, plus some other constant involving this Gauss sum times f. Okay. And if mu is trivial, you get f squared is q squared. And same relation for f1 minus delta, just by symmetry. Okay, so what if we normalize these two generator functions, these two proposed generators? If you normalize them by dividing out by the Gauss sum, then you get the following classical Iwahori-Matsumoto relations. So now we have these normalized functions. You get E delta squared is just Q plus Q minus 1 times E delta. This is exactly from Iwahori-Matsumoto. Okay. And the final result is that this Hecke algebra is really this Hecke algebra for SL2. So what you need to show, it's not clear from what I've said so far that it is, but you have these two generators, F delta and F1 minus delta, and you need to show that these generate the entire Hecke algebra. So if you take products of these things, you don't get something 0, for example, that they really generate this, our Hecke algebra. So our Hecke algebra was supported on these double cosets, which were indexed by the affine Weyl group for SL2, so just the stuff that preserved this middle line, and we want to really generate this entire Hecke algebra. So we let H be the associative algebra, this abstract algebra generated by these same types of generators, T delta and T1 minus delta. satisfying the same quadratic relation. Again, it has the same, this has the same basis as our Hecke algebra. More precisely, if you have some reduced expression, W delta, remember W delta is reflection through this vertical hyperplane, W1 minus delta is reflection through this neighboring hyperplane. This is what TW is, just T delta, that's what I'm, this is definition, T delta, T1 minus delta, T delta, et cetera. And we want to show that the canonical map from this abstract Hecke algebra to our Hecke algebra, which sends its generators to our proposed generators, is an isomorphism. That's the goal. And you need to just prove some small lemma about our functions EW, so products of E delta, E1 minus delta. You need to show some lemma about these products being non-zero, as I said before, and they should be supported on a single double coset. So EW, if you take this shortest expression, is supported on this double coset KWK. Anyway, that's, there's something to prove there. And you finally get that this abstract Hecke algebra and our Hecke algebra are the same. Okay, a couple minutes. So this is the last slide. Okay, so what about this other Levy GL2? Well, I'm still working on this, but the quadratic relation ends up being the same thing. So at least I can say something about the quadratic relation. It's just there are going to be two generators for the Hecke algebra, and they satisfy under some conditions. So remember, the condition that gave you these Iwahori-Matsumoto relations was that this character mu was, I guess, non-trivial. And we need some other, there are going to be two cases again for this other Levy. Anyway, you get, for one of these cases, you get the classical relations, Q plus Q minus 1 times this generator. And similar thing is going to hold for higher rank groups. So I had this sort of general setup with K plus and K double plus, which we're hoping is going to work for higher rank groups. But one thing that I can say is, at least for higher rank symplectic groups, if you take, so we have this Levy SL2 cross GL1, you can take an analogous Levy, SP2n minus 2 cross GL1. That's some analogous Levy in higher rank symplectic group. And you're going to get, there's really not much to do to generalize to this analogous Levy. You're going to get the same Hecke algebra. So this SL2 type Hecke algebra with these quadratic relations. So there's not much to, this SL2 cross GL1 picture really generalizes nicely to this higher rank Levy, the analogous Levy. Okay, that's all. Thanks.